Als erstes wird Professor Dr. Nir Shaviv vortragen. Er ist israelisch-amerikanischer Physiker am Raka-Institut für Physik der Hebräischen Universität Jerusalem. Shaviv schloss 1990 am Israel Institute of Technology in Haifa seinen Bachelor als Jahrgangsbester ab und erlangte 1994 den Master of Science in Physik und 1996 seine Promotion. Innerhalb der Astrophysik ist er besonders durch seine Arbeiten zur Eddington-Grenze bekannt. Er zeigte, dass astrophysikalische Objekte heller sein können, als die Eddington-Grenze vorgibt. Er konnte dabei den Masseverlust bei der Eta Carinae und bei den klassischen Novae besser deuten. Seine Arbeiten über den möglichen Zusammenhang zwischen kosmischer Strahlung und dem Klima sowie der Spiralarme der Milchstraße und den Eiszeiten sind auf große Resonanz in der wissenschaftlichen Literatur und den allgemeinen Medien gestoßen, insbesondere natürlich auch bei uns. So, ich heiße Sie herzlich willkommen, Professor Dr. Nir Shaviv. Er wird berichten über das Verständnis des Zusammenhangs zwischen kosmischer Strahlung und Klima anhand experimenteller und empirischer Daten. Thank you very much.
Thank you for the kind introduction, and thanks for the organizers. I want to concentrate today on the effects that the sun have on climate. What I want to convince you is that the sun has a large effect. It's very important. You need to understand the effect that the sun has if you want to understand what has been going on over the 20th century, and also if you want to understand what will happen with the climate over the 21st century, because if you take the sun into account, or if you don't take the sun into account, you reach wrong conclusions. So basically, this is a summary of what I will want to try to convince you. One is that the sun has a large effect on climate. And then if you look at the 20th century, it implies that somewhere between half and 2/3 of the warming over the 20th century is because of increased solar activity. This goes hand in hand with the fact that the climate sensitivity, which you heard about before, and I will dwell on it again, the climate sensitivity, namely how much the temperature is going to change if you, for example, change the amount of CO2 or other radiative forcing, this climate sensitivity is on the low side. If you double the amount of CO2, it should be somewhere between 1 and 2 degrees. And that implies that future warming, as Professor Scafetta mentioned before, is going to be relatively small. And then I'm not going to dwell on the mechanism itself. What I'm going to show you is that you necessarily need to have another mechanism which is unrelated to the total solar irradiance, because we can see that the effect that the sun has is much larger than just changes in the total solar irradiance. And that mechanism, now after 20 years of research, is the fact that cosmic rays govern the amount of charge in the atmosphere, and that affects the cloud cover. And this will be the subject of my colleague, Professor Svensmark, who will be talking just after me. Okay, so let's first concentrate on the first part, which is the fact that the sun has a large effect on climate. Okay, images courtesy of DALI, the AI. Okay, so the sun is a variable star. It changes its total solar outputs over time, but it also manifests itself in other forms. For example, here you can see what it looks like in X-ray. Sometimes it has more sunspots, sometimes it has less sunspots, it has more UV, less UV, stronger solar winds, weaker solar wind, and so forth. And these things, which we call solar activity, as we shall see, have an effect on climate. Okay, here you just can see what a sunspot look like. This is like the footprints of strong magnetic fields, and this kind of variability changes on the 11-year solar cycle. Basically, what happens is that every 11 years, the north and southern magnetic poles of the sun flip polarity. But overlaid on that are long-term secular variations in solar activity, and all these variations translate into changes in the climate. Okay, this is, I think, one of the nicest graphs showing you how the climate is affected by solar activity. On the top graphs, what you can see is carbon-14 reconstructed from tree rings. Basically, you look at different depths in the tree. You can count the rings, so you know how much carbon-14 was captured by the tree as a function of time. And you can use that to basically measure what is the flux of carbon-14 production in the atmosphere, which is produced by cosmic rays, which are modulated by the solar wind. So basically, on this time scale of several thousand years, the top graph is a proxy for what solar activity is doing. When the sun is more active and it has a stronger solar wind, there are less cosmic rays reaching the Earth and less production of carbon-14. On longer timescales, you also have modulations because of changes in the terrestrial magnetic field and things like that. But on these short timescales, relatively short timescales, it's all due to solar activity. At the bottom graphs, what you see is the ratio between oxygen 18 to oxygen 16 in isotopes coming from stalagmites in a cave in Oman, in the southern Arabian Peninsula. And basically, this is a proxy for the temperature of the water in the Indian Ocean. Okay, so you can say maybe the ocean affects solar activity, or probably more likely, solar activity affects the temperature of the ocean. Okay, so I don't know whether you think this is a nice correlation or not. I think it is a pretty amazing correlation. Okay, here is another example, this time coming from the northern Atlantic. You again see in blue the carbon-14 reconstructed from tree rings on timescales of several thousand years. But in black, what you see is evidence for sedimentation in the seafloor, basically of what's called the ice-rafted debris. During periods when it is colder, you have icebergs floating further south, and when they melt, they leave their debris further south. For example, in 1910, when it was colder, you had the icebergs floating further south, as the passengers of the Titanic noticed, a little bit too late, and the debris was left relatively south. Nowadays, for example, it's warmer, so you get this kind of debris further north. Okay, so this is an example of a core dug from the seafloor, and from that you can reconstruct the climate, in this case of the northern Atlantic, and again see that you have a nice correlation between solar activity as manifested in the carbon-14 and the marine record. Okay, on shorter timescales, you have other evidence. While this kind of graphs are qualitative, they show you that there was some temperature change in the Indian Ocean, or whether it was colder or warmer in the northern Atlantic. There are actually, on shorter timescales, you have records from which you can really quantify the effect that the sun has. Here, what we see in red, we see the solar activity. So you can see the 11-year solar cycle. Which is reconstructed. I mean, it's not direct measurements of the solar constant because we don't have direct measurements 100 years ago. So it's based on proxy records, but still you have an estimate for what the solar output was. You can see the 11-year solar cycle. And in blue, you see the rate of change of the sea level as reconstructed using tide gauges. Basically, what happens is that on short timescales, most of the change of the sea level is due to thermal expansion. The oceans absorb heat, and they just they rise and they fall together with the solar activity. So you see, when the sun is more active, the oceans expand, and when the sun is inactive, the oceans shrink. And the nice thing is that you can use that in order to quantify the amount of heat that goes into the ocean every solar cycle. Okay, and it's about 1 watt per square meter, which is almost an order of magnitude more than the changes that you have in just the total solar irradiance. So this is the first indication that shows you that you must have another mechanism linking between solar activity and climate, because just the total solar irradiance cannot explain it. which takes us back again to what Professor Scafetta said previously in his talk. So this is based on data which goes up to the year 2000. We later looked at satellite altimetry data, and with satellite altimetry data you can again see that you can look at the height of the sea level. So this is the height of the sea level with a linear trend removed, because the oceans are rising because it has been becoming warm and sea level is rising. So if you remove the linear trend, basically the sun and El Nino explain by far almost all the variations that you see in the sea level. Just for the fun of it, yesterday I plotted more recent data with satellite altimetry. The previous graph goes up to 2010. You can download more recent data, and you can see that even the more recent data continues exactly as you would expect. Basically, when during solar maximum, the oceans rise. When during solar minimum, the oceans shrink. Okay, so we clearly see the heat going into the ocean and out of the ocean every solar cycle, and it's very large. This is another type of data. This is using buoy data from 1955. You can calculate the amount of heat that the oceans have. And if you differentiate it, you can basically you see that in the blue curve, you can see when heat is going into the oceans and when heat is leaving the oceans, and you can compare that to solar activity and again see that every time that the sun is active, heat is going into the oceans. You can also see that with the temperature of the oceans. Here we have two examples. You can just take the average global temperature and fold it over the solar cycle and then calculate what is the change in the temperature, what is the temperature of Earth as a function of the phase in the solar cycle. And you see that during solar minimum, the temperature is lower, and during solar maximum, the temperature is higher, and the peak-to-peak amplitude is about 0.1 degrees Celsius. You might think that 0.1 degrees Celsius is very small, but in fact, it is a huge amount. Why is it huge? Because it means that the whole mixed layer, at least the mixed layer of the ocean, has to heat or cool by 0.1 degrees. And if you multiply by the heat capacity that this mixed layer has, you reach again a value of about 1 watt per square meter variations during the solar cycle. And again, this is almost an order of magnitude more than just the variations in the total solar irradiance. Okay, so just by looking at the surface, at the temperature of the surface of the oceans, you can see that a lot of heat goes and leaves the ocean every solar cycle. Okay, one indication for where it might be coming from is the work of my colleague Svensmark, and that is that it's due to changes in the cloud cover. Here we see variations in the low altitude cloud cover, and you see that in I mean, the graphs look very similar, so I cannot distinguish between them easily. The blue is the cloud cover because it starts later than the cosmic rays. So the blue is the cloud cover, and the red is the cosmic ray flux. And you see that basically when the sun is inactive and the cloud cover is let's see, it's inactive here, for example, the cloud cover, the cosmic ray flux is higher, and the cloud cover is higher. Now you can use things like the Earth Radiation Budget experiment to translate these variations in cloud cover into changes in the energy budget, and you find that it's about 1 watt per square meter. Okay, so this should be compared with what we have seen yesterday, changes in the total solar irradiance. So indeed, as was mentioned a few times, it's very hard to know what is the absolute calibration of the solar flux, but we can measure the relative change in the solar flux, and the relative change in the solar flux is around 1 watt per square meter for a meter facing the sun. However, if we average it over the whole Earth, we have to divide by 4 and multiply by 1 minus the albedo, we get that this 1 watt corresponds to less than 0.2 watts per square meter when averaged over the whole Earth. So these are the variations in the total solar irradiance, but as I have shown you, you can look at different data sets, and the different data sets, whether it's the tide gauges record, or the sea surface, or the ocean heat content, or the satellite altimetry, they all give you that the peak-to-peak variations in the heat going into the oceans or into the climate system is much larger than just the changes in the total solar irradiance. So on short timescales, we know for sure there must be another mechanism responsible for linking between solar activity and climate. Now, on long timescales, I don't know, maybe the suggestions that were mentioned by yesterday, where is he? Somewhere. But there are larger variations in the total solar irradiance than what the IPCC is quoting. But even if those kind of variations are absent, we still know that long-term variations in solar activity exist, and they should manifest themselves as long-term variations in the climate. Okay, so we require an amplification mechanism, and today, after 20 years, we know what it is, and Svensmark is going to talk about it after I finish boring you. Okay, so this is what the IPCC says is the effect of the sun. So these are the changes in the Earth's radiative forcing due to solar activity, and it's relatively small. What that means is that when you ask people in these mainstream climate community, they say, oh, we do take the sun into account. Why do you say that we don't take the sun into account? They don't take the sun into account. What they do is they take just small changes in the solar irradiance, which we know are incapable of describing what we really see. We really see that much more energy goes into and out of the climate system than just changes in the solar irradiance. Okay, so what we can do, we can look at other proxies for what the solar activity has been doing. For example, we can look at carbon-14 and beryllium-10, which are cosmogenic isotopes formed by cosmic rays. However, these cosmic rays are modulated by solar activity, so we can reconstruct what the sun has been doing over timescales of, say, decades to millennia. And you can see that we can see the little ice age when the sun was inactive, or the recent activity of the sun, and so forth. So we can use that together with the quantification that we have, the empirical quantification that we have for what the sun is doing, using the heat that goes into the ocean. When we use the ocean as a calorimeter, we can quantify the effect that the sun have. We can then use such proxies to understand what are the long-term variations in solar activity, and then we can calculate what is the contribution that natural solar variability had on the climate. So this is from the fifth assessment report. This is the standard picture for what the different climate drivers are. And here you see this minuscule value is what they say is the contribution that the sun has had. But in reality, if we take what I have just shown you, then this should be the value. Okay, and it's completely ignored. Now, why is it crucial to take it into account if you want to understand what has been going on over the 20th century? Because if over the 20th century, the warming that we have seen is due to basically double the radiative forcing, it means that in order to fit what we see, we need a climate which is significantly less sensitive. And if the climate is significantly less sensitive, it means that future warming from the same given scenario is going to be much more benign. Okay, so maybe just a few words for what the real link is. The real link that we know is taking place based on a range of experiments and theoretical results and a lot of empirical evidence is the following. I mentioned the cosmic rays because they produce the cosmogenic isotopes, but it turns out that they are also the driver themselves. And the reason is that cosmic rays are the dominant source of ionization in the atmosphere. And these ions today play a role, or several roles. One of them is in the nucleation of very small aerosols, which later grow to become the cloud condensation nuclei upon which a water vapor can condense when we reach 100% humidity. And we know of two additional processes that take place which increase the survival of these cloud nuclei or condensation nuclei. As they grow, the charge in the atmosphere help them survive the growth process without being eaten by large aerosols. So then what happens is that when the sun is more active, we have a stronger solar wind, we have less cosmic rays, less ions in the atmosphere, less formation of cloud condensation nuclei, less of them survive the growth process, so we get less cloud condensation nuclei in the atmosphere when the sun is more active. Now, when you have less less cloud condensation nuclei in the atmosphere, when you reach 100% humidity and you want to condense water vapor, you will have clouds which have fewer cloud droplets. These clouds are going to have a larger a smaller surface to volume ratio. Again, we have fewer cloud condensation nuclei, so we're going to have larger droplets which reflect less of the sunlight because they're much fewer. And it means that more of the sunlight is going to penetrate the system. Okay, and today we have empirical evidence for everything, and we can also go to the lab and see the mechanisms taking place. Okay, so I hope I convinced you that the sun has a large effect on climate and that we can quantify it. Next, I want to talk a little bit about the 20th century warming, what I've mentioned. We can actually build a model where we allow the sun to have a large effect on climate. So this is a work that a student of mine did more than a decade ago. Basically what he did, he built a model. He took a model which was developed by Professor Linzen from MIT, and but also added the possibility of affecting the cloud cover and the energy budgets. And one of the interesting things is that the climate sensitivity was left as a free parameter which we can play with and see what is the required climate sensitivity and what is the required solar forcing and so forth to explain, for example, the 20th century temperature change. So it turns out that you can build a completely reasonable model which can explain what has been going on over the 20th century with a residual which is much smaller than what you get with standard climate models. And the reason is that standard climate models don't take the sun into account. And therefore, they cannot explain things like the temperature decrease that you had between the 1940s and the 1970s, or other things which I'll mention in a second when I'll discuss climate sensitivity. So we can fit the 20th century very well, and this fit actually requires a climate sensitivity which is on the low side. Why is that? Again, it's because the total forcing that we now have over the 20th century is basically twice larger, which means that in order to explain the 20th century, we need a climate which has a low climate sensitivity. Then we can generate many realizations for what will happen over the 21st century, and then under standard, this is a vanilla flavored scenario where which is basically a business as usual, you get warming which is relatively modest, of order 0.15 degrees per decade. Okay, so the fact that the sun has a large effect on climate allows you to better explain the 20th century, and it does so with a lower climate sensitivity. So then comes the question, why is the climate sensitivity low, or what is the problem with the mainstream view for the fact that or the mainstream climate view that the climate sensitivity is large? Okay, so a few words about climate sensitivity. Climate sensitivity is basically the response of the climate when you have changes in the energy budget. For example, if you double the amount of CO2, the canonical value is that you will change the energy budget by 3.7 watts per square meter. If you ask Professor Happer, he will tell us that it's a little bit less than that. He found around 3. That's the calculation that he did in his head and showed us, or the 1%. If we take the standard value for what the change in energy budget associated with CO2 doubling, the question is, what would be the warming that we are going to have for the climate? Will it be 1 degree, or will it be 5 degrees? So the climate sensitivity is basically this ratio, the change in temperature versus the change in energy budget. But the more physical view of it, if you're a physicist, you basically care about what are the processes that govern this value. And the way to look at it is actually the opposite. Suppose we change the energy budget by some value. We want to ask the question, how much do we need to change or what will happen is that the surface temperature, for example, is going to change by a given amount, and then you're going to have different processes that will change the emitted radiation, that will try to compensate for it. So the climate feedback is basically the opposite of the climate sensitivity, and it describes the physical processes. It tells us if we change the sea surface temperature, for example, by how much will the energy going back to space is going to change? Will it be large, and then we need a small temperature variation in order to compensate changes in the energy budget? Or will the change in the energy going back to space, is it going to be small? If it's small, it means that we are going to need a large change in the surface temperature in order to compensate for that. So you heard over the past 2 days climate feedback, and the climate feedback is basically the opposite of the climate sensitivity, and it's easier for us, for physicists, to look at it this way, because we can then separate it into different processes responsible for changing the energy flux. Okay, so this is now the climate sensitivity that you find in the IPCC reports. They tell you, or for many years, it was roughly 1.5 to 4.5 degrees, and this was based on climate models. Actually, it wasn't. It was based on a federal committee that convened in 1979, the Charney Committee. They sat and they said, we think climate sensitivity is between 1.5 to 4.5 degrees, and for many years, and many billions of dollars and euros and whatever, it stayed that way. More recently, they said, okay, we can maybe use, we cannot use the climate models to constrain it, so maybe we can use other things like look at paleoclimate and things like that in order to better constrain the climate sensitivity. So what's the problem with the models, and what's the problem with this kind of proxy determinations of what the climate sensitivity is? The problem with the models is that they are inherently, okay, in computer science there's something which is called, this methodology is called GIGO. It's garbage in, garbage out. Basically, the largest uncertainty that you have in the climate models is related to what Professor Klausner said yesterday, and that's the clouds. It turns out that nobody knows how to calculate what the cloud cover change is going to be. So if we double the amount of CO2 and we change the energy budget by 3.7 or 3 watts per square meter, we're going to heat the oceans, and then the oceans can change their temperature by whatever in order to compensate this 3.7 watts. However, if we warm the oceans, there are going to be feedbacks in the system. For example, we're going to have more water vapor in the atmosphere, maybe, and that is another greenhouse gas, and that will cause further warming. On the other hand, if you have more water vapor in the atmosphere, you can also have more clouds, and the clouds can heat and they can cool and they can do a lot of things. And it turns out that nobody knows how to calculate what the cloud cover is going to do. And basically, all the climate models have some kind of recipes which describe the change in cloud cover, and the climate sensitivity that the models get basically depends on this recipe that they plug into their models, which describes the cloud cover. Whether it's more explicit or implicit, but it's still a recipe. And you can see that very clearly in this beautiful graph that dates back to 1989. It shows you the climate models that we have had back then. You see here what is the climate sensitivity, or what the more physical number is, the total climate feedback is. And you see that all the different models lie on this, close to this straight line, which tells you that if you know what is the feedback through clouds, what is the change in energy budget associated with the cloud cover change when you change the temperature of the Earth, if you knew this number well, you would know what is the climate sensitivity. Okay, so basically, the clouds is the change in cloud. It's the big joker card that can basically change what the climate sensitivity is of the model. And if you don't know that, then your model cannot predict the climate sensitivity. So this was in 1989, and nowadays it's still it's similar. What we see in the graph here is separating the total feedback into the different processes that the climate have. If Earth would have been a pure black body or gray body, then what we would have had is what's called what they call the Planck, or what Professor Klausner mentioned yesterday should be called Stefan Boltzmann feedback. This is just the black body, differentiating the black body radiation law. These are additional feedbacks that you have because the atmosphere will have more absolute amount of water vapor when you heat it. You might change the albedo of the surface. You might change the clouds, and then you can have other additional biological feedbacks and so forth. So basically, the total feedback is the sum of the different mechanisms that you have. And you see that even today, the largest quoted error bar is that of the cloud feedback. And this is the feedback that they say that if you take the 1989 Tsess et al. Paper, which shows you that, I don't know what, 30 years later, we didn't reduce the largest error bar in the estimate for climate sensitivity any significantly. In reality, I think it's actually even the error bar is larger. Okay, so basically, climate models cannot predict the climate sensitivity because they cannot describe clouds properly. Nobody knows how to describe clouds properly. And then comes the question, what about the paleoclimatic or other type of empirical records from which you can extract what the climate sensitivity is? Just before that, if you don't believe me that clouds is the joker card, that basically you can get whatever you want with it, this is an example of several models which appear in the CMIP cluster of climate models, trying to predict what would happen or what would Earth look like, or sorry, in this case it's an aqua planet. If you remove all the lands, you're supposed to get something which is easier to predict. what you see here is the change in precipitation and in cloud radiative forcing, and you see the different models give you completely different predictions. Basically, it tells you that you can get whatever you want just by choosing the right model. Okay, so models cannot predict the cloud cover variation. Okay, so what about empirical evidence? What you can do is try to estimate the change or the climate sensitivity by looking at historic variations in the temperature and in the energy budget. For example, 50 million years ago, Earth was much warmer than it is today. The Eocene optimum. There was a change in the energy budget since that time, change in the radiative forcing because of I don't know what the atmospheric composition was different and so forth. So you can use that to empirically determine what the climate sensitivity is, and you can play the game twice. You can play it first if you include the effects that cosmic rays have on climate, and you can do it when you exclude the effects of cosmic rays, whether directly because our galactic environment has been changing, or whether indirectly because of solar activity. And it turns out that once you take, if you exclude the effects that cosmic rays have on climate, you find that different timescales imply, or changes in the energy budget and temperature on different timescales imply that the climate sensitivity can range by quite a lot. However, if you add the effects that the sun has and the effects of cosmic rays, you consistently get roughly the same climate sensitivity, okay, between 1 and 1.5 degree increase per CO2 doubling. Okay, so that tells you that, I mean, it's very suggestive that indeed cosmic rays affect the climate because it allows you to get a much more consistent picture. More recently, we looked at the past 500 million years again, and we found that just by looking at the temperature variations over the past 500 million years, you can fit it very well if you look at the cosmic ray flux variations, the CO2 variations, and the fact that Earth has been, the sun has been slowly increasing its luminosity because it's changing its molecular weight. And again, you get a climate sensitivity which is around 1.5 degree increase per CO2 doubling. Okay, other indications that the climate sensitivity is low were already present. I think this argument was raised by Professor Linzen maybe 20 years ago already. He said they tried to model the response of Earth to large volcanic eruptions, and what was found is that if you take standard models, you find that Earth's response to large volcanic eruptions is much larger than what you see in reality. Here you have the global temperature averaged over the several years preceding and post large volcanic eruptions, and you see that the typical decrease in global temperature is about 0.1 degrees Celsius following a large volcanic eruption. On the other hand, okay, here, for example, when Krakatoa exploded, you had the prediction was, you know, even 0.5 degree or so. In reality, what you see is that the response is small, and that indicates that the climate is not very sensitive. Other evidence, you can look at other empirical evidence to try and understand what the different numbers are. For example, you can look at the clear sky variations in the outgoing long wavelength radiation as a function of the surface temperature, and if you take then the present temperature, you can see what should be the climate sensitivity, or at least the feedbacks, when you take the what's called the Planck and the water vapor response. So this is the clear sky feedbacks. So this plus that you can measure to be this value. So it's, you know, roughly consistent. Maybe the sensitivity is lower or the feedback is larger. You can also look at what happens when you also have clouds. So you can try to estimate what is the change in the outgoing radiation, or sorry, the net outgoing radiation as a function of temperature change. And you can play this game twice. You can look at the global temperature the global temperature change from month to month, and the change in this flux. And you can play this game twice. Once you can look at the total temperature anomaly versus the flux anomaly, or you can look at the variations between a month to month. Like you wait 1 month, you see how much the temperature changed and how much the flux changed. And if you do that, you basically measure the total feedback that the climate system has in response to changes to the temperature. So that should be the sum of all the fast components that you have here. So maybe some of the, the surface albedo might not be part of it, or some of the biological or biophysical response might not be part of it. But the sum of it should be somewhere between these two values. So the total climate sensitivity, or the total feedback should be somewhere in this range, which implies a climate sensitivity which is below 2-degree increase per CO2 doubling. Now, I can give you good arguments why this is correct, and I can give you good arguments why this is correct, which means that I don't know where exactly to cheat between those two limits, but that means that empirical determinations of climate sensitivity should be in this range, namely a small response to doubling or a large climate feedback. Okay, so the climate sensitivity is low, and that also implies that future warming should be benign. As I told you, we can fit the 20th century, then we can integrate what will happen over the 21st century, and we get that the temperature increase should be relatively modest, and this can be compared to different IPCC models. This is relatively old, but the picture is basically the same. And we can also look at what has been taking place in reality. This is the low troposphere temperature as measured with satellites. So this is the University of Alabama in Huntsville temperature, lower tropospheric temperature measurement with satellites, which is much more reliable than the surface thermometer measurements. And you can basically see that the temperature has been increasing by roughly 0.15 degree Celsius per decade, which is what we expect when we do the modeling and include the effects that the sun has. Okay, so basically this is the whole picture, and I will end with a quote which is about 2,700 years old. What has been is what will be, and what has been done is what will be done, and there's nothing new under the sun.